this class, I will discuss with you Newton's law of gravitation. And before I go into the detail of this law, I will also like you to tell the contributions of many other scientists and philosophers which laid the foundation for Newton's law of gravitation. Earliest view of this force was that Earth pulls Sun towards itself, and it is because of this pull that Sun keeps on moving around the Earth. It is just like an object on one end of a string, and if I keep on rotating it by holding the string from the other end, if I keep it moving like this, so the object keeps on moving on a circular path. Sun rises in the east and sets in the west, and next day again it comes from the east and then again goes towards west. So it was thought that Earth is pulling it towards itself, and because of this pull it keeps on moving around the Earth. This was called geocentric theory and was given by Ptolemy about 2000 years back. And this theory was accepted by churches also. At that time, religion, philosophy and science, they were all integrated. They were not separate like it is nowadays. So it had the backing of churches because it was thought that Earth supports life. So Earth was considered to be a supreme planet. All other planets and stars were taken inferior to it, and they keep on moving around the Earth. It was geocentric theory. Another main important thing about this pull is that it is a non-contact force. We have seen so far whenever we push or pull an object, most of the time we find that the objects are in contact. I push this wall by touching it, or I pull it again by touching it. This is a force which is acting from a distance. There is nothing in between them. It is not a contact force. So we call it non-contact force. The pull of Earth on Sun. This is a non-contact force. So geocentric theory, earliest theory to explain the motion of Sun around the Earth. In about 500 years AD, Aryabhatta, an Indian astronomer, he gave theory. He said that Sun is at the center and Earth moves around it. He also explained solar eclipse, lunar eclipse. He also told that the Earth, apart from moving around the Sun, it also moves about its own axis. But this theory given by Aryabhatta does not find any mention in Western literature. Maybe because the communication was not so strong in those days. Copernicus in about 1543 also championed heliocentric theory. Heliocentric theory means Sun is at the center and Earth is moving around it. Geocentric theory means Earth is at the center and the Sun is moving around it. So geocentric theory was given by Ptolemy. Aryabhatta gave heliocentric theory. Copernicus also gave heliocentric theory. He also found the motion of Earth about its own axis. So apart from telling that Earth moves around the Sun, he also told that it moves about its own axis also. Copernicus. But again, since the churches believed in geocentric theory, so he had to face lot of oppositions from the priest. The same happened with Galileo. Galileo also talked about heliocentric theory. Galileo was a very well-known figure, gave a number of laws. He also gave the law of inertia, if you can recall. Galileo also gave heliocentric theory. He observed the motion of Sun and Earth using his own telescope. He designed telescope also. and then concluded that sun is at the center and it is the earth actually which moves around the sun, not the other way around. He also had to face a lot of oppositions from the church. He had to lose his job. He was kept in house arrest and was asked to apologize in public. He did it. There is a very important play, very well known, famous play, and there is a movie also on Galileo. He apologized, but at the end he also said that though it does not change the facts. So he said that, okay, you are saying so earth is at the center and sun is moving around earth, but the fact will remain fact. So it means he believed strongly in heliocentric theory. Tycho Brahe was another astronomer. He lived for a very short span of time. He collected lot of data about the motion of stars. Lot of data he collected, but could not formulate any law because of short span of time. However, the data collected by him was used by Kepler. Kepler was an astronomer who, after studying the data collected by Tycho Brahe, gave the laws of planetary motion. I will explain what those laws were. He gave 3 laws of planetary motion. First was all the planets move around the sun in elliptical orbit, not circular. Before Kepler's, all of them gave the theory of circular orbits. And whether the earth is moving or the sun is moving, they talked about the circular orbits. He told that the orbit of the planets is elliptical. Secondly, he said that whenever a planet is moving around the sun, it covers equal area in equal intervals of time. We call it aerial velocity. So aerial velocity is constant. What does it mean? If a planet is at A and after time t it is at B, so this is the area covered. So in t time it has covered this area. Let this be A1. Now if this planet is here, then in time t it will still cover the same area. So it has to move faster. This area is A2, so A1 is equal to A2. This area is equal to this. Time is same. So any planet in a given time covers same area while moving around the sun. Aerial velocity is constant. So first law was planets moving in elliptical orbit, and second, aerial velocity is constant. And then third, if I take circular orbits, in ellipse we define as semi-major axis, semi-minor axis, major axis, minor axis, that you will do in higher classes. For the time being, I am writing this for you only for circular orbits, or you can say r is the mean distance of the planet. So the mean distance of planet from the sun, if I take it r, or if I am taking circular orbit, r is just the radius. So cube of this distance is proportional to t square. Square of time period proportional to the cube of mean distance of the planet from the sun. So 3 laws. Planets moving in elliptical orbits, their aerial velocity is constant, and third, square of time period is proportional to the cube of mean distance of the planet from the sun. These 3 laws were given by Kepler. Now Newton studied the Kepler's laws of planetary motion and then gave his own law of gravitation. What is it? Now there is a difference. The earlier laws given by Kepler, they were for sun and earth, planets and sun, and the other philosophers studied mainly about the earth and sun motion. But Newton's law of gravitation is a general law applicable to all masses. What it says? Every mass in the universe, not just earth and sun, every mass in the universe attracts every other mass with a force which is proportional to the product of masses, inversely proportional to the square of the distance between them. Proportional means if mass is more, the force is more. Inversely proportional means more distance, lesser force. So if I take 2 point masses m1 and m2 separated by a distance r, then Newton's law of gravitation says that the force is proportional to the product of these 2 point masses, inversely proportional to the square of the distance. So if we remove this proportionality sign, there is a constant, and this constant is called universal gravitational constant. Universal constant means a constant for which the value remains same everywhere. It does not depend on anything else. And the value of this, now see, Newton published this law in the book that I have written here, Philosophiae Naturalis Principia Mathematica. It was written in Latin, and its English name can be said as Mathematical Principles of Natural Philosophy in English. So this law was published in 1687. The value of G, universal gravitational constant, was calculated by another scientist, Henry Cavendish. Henry Cavendish, and this was 1687, and this was done in 1798. So about 111 years after this law was formulated by Newton, this constant was calculated, and Newton's law was experimentally actually verified by Henry Cavendish. So F is G m1 m2 by r square, where G is universal gravitational constant, m1 m2 are the point masses, and r is the distance. Now let me talk more about this. What is the value of this universal gravitational constant, and something more about this gravitational force. G m1 m2 by r square. The value of G was found to be 6.67 into 10 raised to the power minus 11. And what will be the unit for it? Newton meter square per kg square. This we can find from here. And how can we define G? G is F r square upon m1 m2. So if r is 1 meter, m1, m2 both taken as 1 kg, then G is actually F. Using this you can define. So universal gravitational constant is the gravitational force between 2 point masses, each of 1 kg, separated by a distance of 1 meter. Universal gravitational constant is equal to the gravitational force between 2 point masses, each of 1 kg, separated by a distance of 1 meter. So this is how we can define the value of G. Further, see, this force is always attractive. Gravitational force is always attractive, and it is because of this force that whenever we drop anything, it comes down. Whenever I drop any object, it comes down. It is because of the pull of Earth. So Earth does not pull only Sun. It pulls all other objects, and not just Earth. Rather, every mass in the universe is attracting every other mass with some force. So this is always attractive. And X along this line, so on this the force is in this direction, and on this mass force is in this direction. This mass pulls it and this mass pulls it along the line joining them, and it always obeys Newton's third law. So force on first due to second is always equal to force on 2 due to 1 with minus sign. So this is the force on this, and this is also the force on this. Both experience the same force. So this is Newton's law of gravitation. Every mass in the universe attracts every other mass. This constant is also very small, but heavenly bodies, all these stars and planets, the mass is very, very large. That's why this force is not very small. The force acting between the planets, between Sun and other planets, is very, very large. It is because of this force that all the planets are moving around the Sun. So entire solar system, or I will say even galaxies, different types of stars, are having the motion because of the gravitational force. So it is a very strong force which is keeping all the planets attached to the Sun. Another way, Earth, we have ocean, we have mountains, all these things, even the atmosphere, all these things are held because of the gravitational force. If the gravitation is weak, it will not be able even to sustain the atmosphere. It is the reason why there is no atmosphere on Moon, because Moon's gravitational force is less. The mass of the Moon is less in comparison to Earth. Mass is very light. It is so light that it cannot hold even the gases, and there can't be any atmosphere because of that less force. So gravitational force keeps the gases in the atmosphere, and it is because of this force that mountains and water, all these things are attached to the Earth. It is because of gravity. So that's all for this class. I will take now free fall, mass and weight in the next class.